Hello, hello. We are so happy today to have Steve Davies, who is the VP Performance Packaging at NatureWorks, which, as far as I know, Steve is the biggest bioplastic company in the world. So let's start right there.
We certainly were. May not be anymore these days, and that's a good thing. As more folks help us become an industry of many producers, not just one. But I think certainly we had that role for probably 15 years or so, and now there's many other players. We're probably still the biggest, but looking forward to sharing that role and becoming not an industry of one, but an industry of many.
That's wonderful. Thank you so much for agreeing to be on the show. I know our teams have been talking for a while, and I'm glad we could get you on the show.
Oh, glad to be here.
And we're going to start with Steve the person because we did a lot of digging, Steve, and Alex really spent a lot of time but couldn't find much. So tell us about your growing up and what influences you had that led you to what you do now.
Well, that's funny. I didn't mean to be a mystery person. Yeah, your question really about it brought back some really memories of garbage for me and really took me down memory lane. And so I just want to say, hey, thanks for helping me connect the dots. So I'll try and say this quickly. Look, I'm a Brit initially, born in Britain, emigrated here as a teenager. But as a child, young child in the late '60s, growing up in the UK. Look, UK then was what, 2 decades after World War II, and so the adults that I interfaced with as a little kid, that legacy of the war and the deprivation was still very present in the way the adults I respected and that influenced me thought. And so, just to be clear, what I mean is those adults had a mindset of preservation and reuse and fixing things and not discarding them, right? And in their youth, they'd grown up pretty deprived. That food was rationed, butter was rationed, right? I remember my grandmother telling me that. Materials were rationed. So it was a worldview of thriftiness, and that's what I grew up with. And now, to be clear, I didn't grow up deprived. I had a kind of an idyllic childhood, but that was the mindset. And so all that to say that when we emigrated as a family to the U.S., in the '70s, well, look, it was breathtaking. Here was the land of plenty, right? Everything was done on a grand scale. Cars were huge. We were a family that had a little Morris Minor, a Morris 1000 1-liter engine. I stepped off the plane in Charlotte, North Carolina, and I got in the biggest car I'd ever seen, a Chevy station wagon, right? Duh. But there was lots of everything, and there was for sure lots of waste, right? Everything was sort of just, it was profligate. And for this kid that had grown up with this culture of thrift, preservation, reuse, repair, fixing things, it was kind of mind-blowing. I still recall my father, a year or two on, we went back to the UK and he was talking to my uncle in the UK, and he was marveling at this electric drill he brought from Sears. And he said to his brother, my uncle, I can't take it apart. If it breaks, I throw it away. There's no screws. And he couldn't get his head around the fact that you couldn't fix things. And it's funny now, I'm thinking, what, 40 years later, who the heck would take apart an electric drill, right? It shows how much I've become a part of the culture. My father is probably rolling over up there listening to me, right? But it shows the cultural difference, how much we have a culture of discard. And so roll forward a couple of years. I'm now a teenager growing up in North Carolina, and I take a trip to the city dump, as we used to call it then. These days we use nicer language, right? The sanitary landfill. But back then it was just a dump. And it was fascinating. We were cleaning house. Some elder brother and I were tasked to just take a load of stuff to the landfill. And we were startled at what we saw there was this tremendous treasure trove of materials. Diverse materials literally being dumped. And on that first trip, we took a station wagon full of trash to that dump. And we came back with a station wagon full. We brought back an outboard motor for a boat. Now, never mind that it was smashed. It had a hole in it. It didn't run. That's why it was thrown away. As my father pointed out when he looked at us and shook his head, he said, boys, we don't have a boat, right? But the point was we couldn't get our heads around somebody throwing away a 200-pound motor and all the value that represented. And so a couple of weeks later, we were tasked to take that back to the dump. Unfortunately, this time we came back with an even bigger prize. We brought back a Coca-Cola machine. You know, this 6-foot-tall, big, red, 4-feet-wide refrigerator that dispenses cold drinks. And when my father came home from work that day, I maybe you'll remember, we had to proudly set up this prize in our screened-in porch. And he came in and we said, Dad, you can fix everything. Can you help us fix this tonight? So, long story short, he took that back to the dump, didn't let us go again because it clearly wasn't working. But I guess this sort of gets to the theme of the question I know you always wrap up on, which is, and we'll come back to this, but what is good garbage? And I think I sort of went into a little bit of detail on my mindset as a little kid, because that wasn't garbage. It was this rich material stream that I wanted to mine. And that's been kind of, I realized when I saw your questions, it really helped me connect those dots and see the whole trajectory of why I am the way I am. So, hey, thank you. Does that make sense?
Yeah. And it brought up so many thoughts and memories for me. And so I'm a very recent migrant into the United States. It's only 3 years. And I was amazed because, again, like, of course, we are in very different times, but everybody wanted me to go to Costco. And then, of course, nothing against Costco, but I'm a packaging guy. It's for me, it's all about how do we leave the planet cleaner. And I just couldn't handle it because there was so much packaging. And I was like, why do we need to put potatoes into a bag? And so I did my membership for a year, probably didn't use it at all. And I said, I'm not going to. And you end up shopping much more. It's the consumption side as well.
Yeah.
Where I realized that although it is cheaper, but you end up with a bigger bill and you buy stuff which you don't need. And, because it's bigger bags, And the other one that came to me very evidently was, my father used to tell me that they used to build go-karts by getting motors from the site. So I was actually hoping you're going to actually take that motorboat and actually create something out of it. And they would go to the local, what we call the guy who collects stuff like that.
Yeah.
And just pick up stuff, pick up heads and pick up motors and, make their go-karts from that. And I'm sure your father banned you from going to the dump after that, after your big refrigerator. But I was hoping that in the end, some Coca-Cola would have come out of that. But I guess it didn't.
It's funny though that you say it because my father did help us take a lawnmower engine, repurpose it, spin it around, and put it on horizontal shaft to drive a go-kart. So yeah, it sounds like we had a lot of the same sociocultural sort of influences as kids. Yeah.
Yeah, and my father did something similar, and he put a similar engine on my bicycle.
Whoa.
And it made the loudest sound. And I remember growing up in this little rural town in India, not even town, a village in India, and there was this one bull who hated that sound, and he would chase me each time. So, and I banged my autocycle, as we used to call it, and I all sorts of things, but and I used to be so scared of that bull, but he was just so annoyed with the sound that engine would make.
That's funny. You don't want to irritate the bull.
Yeah, but okay, let's move forward. And I see that you did a master's in chemical engineering and worked in various places before you end up in NatureWorks. So tell us more about that journey.
Yeah, so I finished high school in the U.S., actually went back to the U.K., going home, I thought, for university for a year, but then realized quickly that, man, I'd grown up in the U.S. and I was more of an American, and as much as I hated to admit it, quite materialistic in my view, and there was more opportunity in the U.S. and more to do. So I came back, finished school here, got a chemical engineering degree because I like making things, and what chemical engineering promised me was a chance to make things at scale, which has been kind of a theme and what got me passionate. We'll talk more about this, about NatureWorks. So I got a master's degree in chemical engineering and then spent some 15 years or so very much in the classical chemical engineering field with a company called Alloy Signal that became Honeywell. Many listeners have probably heard of Honeywell. They think of it as aerospace or your thermostat in the home, but Honeywell had a big materials division, fibers and plastics, performance materials. And I worked there in many different classical chemical engineering roles, process designing big reactors. At one point, I remember my claim to fame was I was leading the process design group for the world's biggest factory making the building block for nylon 6 for carpet fiber. Many nylons out there, nylon 6 has a huge price in carpets in the home and many other uses in engineering plastics. But this was at a facility that made sort of £1 billion per year of that building block, roughly. And I remember thinking, after being there a while, wow, it's £1 billion a year. We're proudly cranking out, and we have all these boards around the plant talking about production rates, doing it safely, and yet that's essentially back then £1 billion a year of carpet that's going into a landfill. And it didn't, for the idealistic little kid that was trying to pluck stuff out of landfill and bring them home, right, to fix, that didn't jive well. So my time at Honeywell also included a stint in the polyester business, making what the industry calls industrial polyesters. These are high performance fibers for the skeleton of a tire is made out of polyester. Um, the cordage and rope, the seat belts in your car, all high performance polyesters. So grew up running a facility and improving a facility that made those materials. And the whole time was I loved the technical challenge and what I could do at scale to make better things for people. But the whole time there was always this unease that wasn't bugging me a lot, but it didn't. I knew where these things were going and I knew where they came from, right, from fossil materials. And that was in large part, I think, really why NatureWorks, when it came along, was such an exciting opportunity for me.
And how did it come along? How did that? Because I know you've been there for 20 years. It's a while, and so how did they come, and how did they keep you there so long?
Yeah, it's a good question because 20 years, it's staggering when I think about it, especially in this day and age when people have sort of 10 jobs in that time period, right? I'm a dinosaur. Um, so I was quite having a lot of fun at then Honeywell, beginning to look at wanting to do other things. And a recruiter came to me and said, "Hey, I've got this opportunity." It was then Cargill Dow, a joint venture between Cargill and Dow. Cargill bringing the biotech, Dow bringing the expertise in building world-scale plastics facilities. So it was a good marriage, natural one. And what immediately got me and grabbed me literally, I had a literal, visceral, gut level reaction when talking to this recruiter, and it doesn't happen much, right? But here, my reaction was saying to myself, hey, here finally is the chance to do all the same things that I'd done for the first 15 years or so of my career, making cool, useful things that address people and society's needs, but to make those things in a better way, to make products that fundamentally are different because they come from somewhere else and they go somewhere else, meaning they don't come out the ground from an oil well head. They're bio-based, and we'll talk more about the big picture behind what that really means. And there's some new possibilities of where they can go. Because I know as a society we talk about throwing stuff away, and the question is, where's away, right? What does that mean? So I loved the possibility that here was something that I could, with this new material that then Cargill Dow, now NatureWorks are making, PLA, that it could be deconstructed back to the building block. It could be recycled. Could be composted, degraded. So those possibilities were really intriguing to me, and it made it a no-brainer. I came right out and interviewed and came away thinking, whoa, this is a place where I can marry that starry-eyed idealism of the little kid that was, that grew up in the UK, and then the adult that wanted to make a difference at scale.
Yeah, that's wonderful. And I didn't realize that NatureWorks had been around for so long till I watched during the research, just till I watched the
Mm-hmm.
website video. It was
Mm.
1989. So tell us more about
Yeah.
how NatureWork idea came, who founded it, and how did it evolve initially, and
Sure.
then to
Yep.
the place it is now.
Yeah, so back in '89, it was really nothing other than a cool idea in a Cargill lab as to what could I do with the carbon that was captured as a greenhouse gas in plant sugars. What could we do with that? Cargill as a business looking to do things with the material that it was processing. And Cargill at that time, and still today, a huge processor of essentially industrial corn, field corn, was generating a lot of starch. Very low value stream. Corn is interesting because it generates, and we're not talking here sweet corn that people eat, we're generating industrially purpose produced corn, field corn, that makes corn oil, from which you can harvest proteins, a whole raft of things. But about 50% of the product is starch. It's very low value. And the farming community, partnering with Cargill, was really interested in doing more with that product. And so the lab idea that took about a decade to sort of materialize and manifest was to understand and develop a way to ferment that sugar into something useful. And fermentation, we all know as consumers, right? It's the same process that makes beer or wine. But our fermentation doesn't make alcohol. It makes this species called lactic acid. And it's something that I looked at the stat at one point. You probably know it well. The body makes lactic acid. It's what I get when I work out, it's what burns. I don't remember the exact number, but I think our bodies produce on the order of half a pound a day. I feel like mine makes a lot more, as out of shape as I am. But what we've done and what Cargill did in that lab from sort of 89 to 99 is industrialize that process so that we could make it at thousands, in fact, hundreds of thousands of tons per year scale to be a building block that could go many different places. The first use has been a building block to just link the lactic acids together in a long chain, polylactide, as it's called.
And that's an amazing innovation. So was there a person behind that who had this idea? Because it sounds pretty complex, and of course we're going to get into more of the intricacies and would love to learn more. But tell us more about the inspiration behind this.
Yeah, that was certainly a huge team. Clearly, the person that probably was the face of it to the public was a guy named Pat Gruber, who hired me into NatureWorks. Tremendously passionate guy and good at taking these interesting ideas and pushing them through, because I've saw this in prior career, that anytime there's a new idea, it's a huge sort of inertial hurdle to overcome, to build the business case, to get the capital, to build the plant, to then develop markets. And it's innovation's hard at scale, and the Pat really crusaded and was a very effective crusader for what became NatureWorks today. So he was really, I think, the genesis behind Cargill recognizing, okay, we've got this cool biotechnology, but Cargill, massive and clever as it is with its multiple abilities, is not a company that had then the ability or the know-how to scale, to build world-scale plastics factories. That's where Dow came along in a very natural joint venture back around 2000, 2001.
And is it still part owned by Cargill, or it is totally owned by Cargill? How does that work?
Yeah, Cargill has been a wonderful sort of parent owner consistently from the beginning, since that idea came out of the lab. So consistently 50% owner. From 2011 onward, we've had another great owner out of Thailand, PTT, GC, Green Chemical. And their interest, perhaps it's obvious, but Thailand is today the world's second largest exporter of sugar. Sugar is a bit like starch, an agricultural commodity. Thailand would love clearly to export a higher value added product and to do more with its sugar. And here was a chance to bring the industry, the biotech industry, to Thailand, and it's now become real. And we could talk more about this with the build out of our second facility to make NGO at a world scale in Thailand, slated to start up in a 2025 timeframe.
Yeah, and I'm very excited to hear more about that. And I saw that it was 75,000 tons, so that's
Exactly.
significant
Yep.
capacity. But before we get there, I want
Sure.
to dig a little deeper into the technology, because it sounds really, really fascinating that, what you say, that you derive a
Mm.
lactic acid. And what I'm also fascinated is the polymerization process.
Mm.
If I look at starch, and then the modification to lactic acid, and then of course polymerization. So it'll be great to just learn a little more about how that process works and how does it become NGO in the end.
Sure. Yeah. So I'll preface this by saying I'm a long way from my chemical engineering and certainly my chemist roots. So this is going to be a layman's explanation. But what starch is essentially a long chain sugar. That we start by taking, in this case, in Nebraska, where we're producing today, we break down the starch with water to back to dextrose, to a sugar. So that sugar is chemically not a whole lot different than the sugar from sugarcane. And so the point here, and the point that got me excited, really going back to how I came to NatureWorks and that recruiter calling me, was this big idea that you could go to any geography in the world and use whatever was the locally abundant feedstock. What it happens to be in the US is starch. What it is in Thailand, as I said, second largest exporter of cane sugar, is sugar. What it would be in Europe could be sugar beet. So here is nature serving up, to us, a sugar, whether it comes from sugar beet, sugar cane, or corn starch, that is sort of designed as a fermentation feedstock. So wherever that sugar comes from, there's subtle differences perhaps in the fermentation efficiency, but either way, at the end of the day, fermentation produces not alcohol, but this thing called lactic acid, which is a pretty simple species. And the polymerization is as simple as making them hook together end to end with the right catalyst, and then controlling the chain length, which affects the viscosity, the flowability of the polymer you make. Chemists would call it molecular weight. And that has a huge impact on whether you use it to make a sheet for a cup or a clamshell, or a high-performance fiber for carpet, or a non-woven fabric, a fabric for a diaper, for example, or a big filament for 3D printing. So we control all of that with the two knobs we use when we make the polymer, the molecular weight, the chain length, but also going back to the lactic acid species, this is a species that exists naturally in two different formats, mirror images of each other, sort of left-hand, right-hand format. And they behave identically, but when you put the two together, you can have a strong effect on the property of the polymer you make. And so with these two control knobs of, if I imagine two dimensions, chain length, molecular weight, or the mix of the two monomers, the left and the right-hand monomers, the way you put those together, we can move the polymer properties around tremendously to make, we have a slate of products, and so to be clear, we sell pellets, these Ingeo polylactide pellets today, that by the rail car in many cases. They're differentiated by the viscosity and the type of lactic acid we use, and it lets us address a huge variety of end markets.
Now there are multiple types of NGO pellets in different grades, and is that what you mean when you say different viscosity?
Yes, yeah, probably a portfolio of products today that's some 25 different grades, some designed for higher temperature use, some for lower, some designed for, say, a high viscosity use to make a fiber or a package, lower viscosity, say, designed for use to injection mold a product where you need a low viscosity polymer to flow into a mold, injected into a mold to make a part. So that is the key differentiator. I will say, though, I think probably one of your questions we often get asked is, look, what distinguishes NatureWorks product from other PLA products?
Sure.
So maybe I could talk about that a little bit.
Yeah, and absolutely. And I had earlier interviewed Thomas Philippon from
Sure.
Corbillon, and then of course that's a very different system as well. So yeah, I would love to learn the differences, and you could take that specific case as well.
Sure. No, and I know Tomas. I mean, we interface at an industry level in some of the associations. He's a super articulate spokesperson, and it's good to have him as well with us speaking for the industry. Maybe I'll start by saying the obvious, that talking about NatureWorks products and distinguishing from other PLA products, I mean, having spent some 20 years at NatureWorks, for most of those 20 years, there were no other PLA products, right? We were sole producer, and it's funny, if you sort of big picture, it can be a bit scary when you try to start a revolution, in this case, a materials revolution, right? Rethinking what we make everything from. Be a bit scary when you start this revolution, you look over your shoulder to see who's following you and see who's rallying behind you as you lead the charge, and you don't see anyone for a while, right? You got to question, are we doing the right thing? Why is no one joining us? So it was hugely gratifying, sort of 15 years on, around maybe probably 2015 timeframe, to see somebody credible, like the company Tomas now leads, TEC, Total Energies Corbion, credibly making plans, and then a couple years later starting up and joining and helping us move, so that from being sole producer, an industry of one, the PLA producer, to now helping us build out a PLA industry. Because clearly, when you're a single producer, you can be sidelined as a curiosity, interesting, but some folks will sit on the sideline and not adopt your material because it's single source. They want to see multiple providers. We get that. And so it was clear that it was time for the industry to grow out with other producers in other geographies, other feedstocks, as we'll be doing when we go to Thailand and start up, and really help move the PLA industry to the mainstream. So that was kind of a big picture, if you will, on the state of the PLA industry. So getting more detailed, though, about, okay, so now that there are this raft of of growing, number of PLA producers, what's different? And I would say, big picture, look, it's clear from a NatureWorks perspective, our asset investment, where we're investing hundreds of millions of dollars in the past and going forward, that asset investment is very much in making PLA, because that's the missing piece. But as we face the market, we've been very clear from the beginning that we're not just going to offer PLA. It's been fair until now, that's been the largest part of our portfolio. But going forward, we plan, and we're doing it today, the Ingeo grades, Ingeo, the name of the products we sell, simple combination of ingredients from the earth, INGEO, right, Ingeo. The Ingeo products we make will comprise whatever they need to. PLA will always be a key piece of that portfolio, but we look to other polymers, ideally bio-based, things like the PHA family, and we can talk more about that because we've got a partnership in that space now. Things like PBS, PBAT, some of the listeners may know these, but it's a raft of things, some of which aren't bio-based, but can be and are becoming bio-based. But the point going forward is we are, if you go back and look at our mission statement, it's basically to be an advanced materials producer, to make materials that provide the function. And so we will use whatever tool we've got in our toolbox to make those polylactides. The PLAs, of course, will be a big tool, and the tool we invest in to manufacture. But we're not limited by what we make. We source other monomers today, combine those to give differentiated Ingeo grades today that do things that a plain unmodified PLA will never do.
Yeah, and staying with the technology side, you said that it could be made by multiple kind of sugar chain products. So, and then different starches, and you mentioned like sugar cane and sugar beet. Does the process differ when you're doing it from corn versus something else, or is the process pretty much similar?
The process is quite similar. The fermentation may be adjusted a little bit to get the right yeasts to handle a slightly different sugar, but the lactic acid produced will be the same chemical species. And of course, it's got to be made at the right purity level and the right, going back to that, the point I made about left and right hand versions of the lactic acid, you've got to be able to make the right amount of each and combine them in the right way. I think we're pretty good at that after 20 years. But essentially from there forward, the polymerization is today fairly similar. It's who can do it most effectively, most efficiently to give the best quality polymer, and then who can differentiate that PLA that's coming out of that asset with other tools. And I mentioned access to the PHAs or PBSs, or a whole raft of things that we can then adjust the properties to make it do what the market wants.
So I live in the area where there's a lot of sugarcane producers and of course sugar producers again. And I grew up in that area. And then
Yep.
A lot of, so what I've been told is that they obviously take their molasses and create alcohol from it. And could they go to the direction of ethanol? Could they go to the direction of lactic acid from alcohol? Is that a methodology and then polymerize it, or does it mean that they have to start from the juice onwards? How does that play?
No, if I understood it right, I think the answer is for sure yes. One doesn't. The molasses is another crude sugar source. One doesn't have to go from that to ethanol to lactic acid. It's simpler. You can take any sugar source, make an alcohol, in your example, ethanol, or you can make lactic acid or other species. And so sugars are being fermented into other monomers today, for example, to use as building blocks for polymers. So we often have, sorry, go ahead.
Sorry, no, go ahead. Go ahead.
I was going to say, we often will get inquiries from different geographies around the world, or sometimes different producers saying, hey, I've got this big waste stream, their language. Could that be used by you to make your material? And we love that question. We take a hard look at it. What often gets missed in the discussion is the scale. What seems like a huge waste stream to a producer, for example, often is small compared to what we need to generate to build a world-class facility, and it doesn't make sense to try and aggregate these low-value streams from different parts of the world and ship them. You really need to co-locate your factory where the raw material is, which is why we have a factory outside of Omaha, Nebraska, right in the cornfields, at a huge biorefinery complex, where there's all these streams value-added streams coming off the feedstock going into the biorefinery. Lactic acid is but one of them. Small piece, probably 5 or 10% of the biorefinery output is lactic acid for us. Same reason we put in Thailand, we're building and we've got steel going in the ground now and now concrete going in the ground. We're locating that in northern Thailand next to the sugar mill. So that it's right there so that we don't have to transport materials around the world. It's a long-winded answer, but does that sort of get at your question?
Yeah, but I do have a follow-up on that.
Sure.
So say taking an example of the Thailand facility, what would you take from the sugar mill? Would it be, what stage would you take your input? Would it be the alcohol, or would it be something before that?
No, it'll be the sugar. The sugar that could
the actual sugar.
Right. It'll be in a liquid form. It'll be in the liquid format. It won't be, refined and crystallized and cleaned up, or not, to give the brown sugar you'll find at your coffee shop, or the white sugar we use for baking. No point to do that. It'll be the syrup, the liquid. That sugar mill might supply that to an ethanol producer in general. I don't believe they do in that geography, but we'll take that stream. And what we like about that facility is there's all this huge cellulosic mass coming in, the sugar cane itself, and that can be used to generate energy to run the sugar mill. So there's energy regeneration going on as well, which is a huge carbon credit in terms of that supply chain.
Yeah, we of course come from the domain of buying that sugarcane waste and creating other things from it rather than burning it. So
sure, no, bagasse is a great product.
Bagasse, and you can use it for other things. So, and how do you eventually? I presume you get a liquidified form eventually of lactic acid, and how does the polymerization happen? How do you convert that liquid into a pellet? How does that work?
Okay, you asked that earlier, and I guess, let me try and peel it apart a little bit. Yeah, that liquid lactic acid goes into a reactor, is heated to a couple of 100 degrees centigrade. There's a catalyst put in, proprietary catalyst, that helps cause the chemical reaction. First, it's a couple of steps. The first is there's something called lactide made, which is basically two lactic acids hooked together to make a ring structure. So many chemists would say that's the monomer we use, lactide. So that lactide is purified in distillation, and because there's different kinds of lactide one can make. We can take two left-hand molecules, right, and put them into the same ring, two right-hand molecules, or you can put left and right hand into one ring. So there's at least 3 different kinds of lactide one can make. We make all of those, use distillation columns to separate them, another sort of clever chemical engineering unit operations. And then those in turn, they're stored in intermediate tanks, and then we'll draw from those lactide tanks the right ratio to make the final polymer. So those lactide streams, which are again liquid, are pumped into another polymer reactor, a couple 100 degrees, different catalyst added, and the rings literally open up and join together. And that's the mystery of chemistry. I was a chemical engineer that liked the plumbing piece of it, not the chemistry piece. So I won't talk more about the magic of the chemistry, but that's it in a nutshell. And the length of time in the reactor can control how long the polymer chains get. And we have other ways to control that as well. So that determines the viscosity. And the other key variable I talked about is controlled by the mix of lactide you use, the left and right hand species. So we get, coming out of the reactor, we cool the polymer in water and make literally pellets, so a couple of millimeter little pellets, packed out, dried, and those are shipped to the customers around the world.
Wow, it must be fascinating. I have to visit you at some point to get my head around what you're saying. But you clearly haven't lost touch with your chemical engineer. But how did that switch happen from chemical engineer to a marketing kind of lead?
I think it was where I saw a chance to make a difference, and going back to the questions you asked up front, it really helped me connect the dots to that little kid and his aspiration about wanting to make a difference, and to what I'm doing now as an adult. And I began to realize, as much as I like designing big pieces of equipment to make stuff as a chemical engineer, especially in a new space like NatureWorks is in, often the missing piece is developing the market downstream. It was not it's not a case now of like at Honeywell, I could help make very good polyesters or nylons, and the market was there and knew what to do with them. In this space, this was a new to the world material that the market would say, what do I need that for? I have to process it differently. And so I saw very quickly I could make a much bigger difference by moving downstream, market facing, and articulating to the customer, the chandler market, all the way down from the guy buying the pellets from us and extruding them to make a fiber or a sheet or to make a clamshell, all the way down to the retailers. I could articulate why this mattered and how it could satisfy their goals. Because I'm sure, as you know well, our listeners will know, now most retailers around the world have very ambitious goals, sustainability goals. Of Walmart, a good example. Some very well articulated goals of how many hundreds of thousands of tons of carbon reduction they want to drive. That can't happen by doing the same thing. Part of the way it can happen is by using different materials that cause less carbon generation, carbon dioxide generation.
That still doesn't answer my question, though.
Go on, ask it again.
You gave me a whole spiel on the qualities that are needed, but why did you switch to being a marketing person? Like, of course, you wanted to promote that idea more, but I presume there has to be a switch at some point, and you say, okay, I'm going to try and promote this material instead of create this material.
No, fair enough. I sure didn't mean to skip the question. And that switch happened even back at Honeywell. I was moving into more and more of a downstream role, working with customers, because I think it's a natural progression that many go through. I heard the interview with Tomas Philippon, and same thing he went through, is sort of moving from chemical engineer downstream. It's where you can see you can make a difference, and working more and more with customers, I think, is a natural progression. So it just continued at NatureWorks.
And I guess that helps, right? When you are in such a technical industry and you understand the technology and you can relate it back to the people back in the plant and you speak their language, I guess it helps both ways, to the customer and to the plant itself.
Yeah, I think for many of us in this role, we become translators from the technologists who are darn good at what they do, to the manufacturing people. They're very good at translating into making things. We help translate and connect them to the market that's interested, and that's hugely rewarding. And as much as I liked designing chemical reactors, designing polymer reactors to make some of the world's biggest nylon reactors, for example, as much as that was fun, it's even more rewarding to be the translator that helps connect technologists, manufacturers, our people that make the polymer, and the market. And so why did I switch? It's more rewarding. I mean, it's simple as that. Does that answer the question?
Absolutely, spot on. Okay, let's move to the applications. What I saw was fascinating on your website, where there's so many applications that you guys have gotten into. It literally felt like anything that plastic could do, PLA could. So how do you guys evolve the applications? How do you choose that this is what we are going to get into? And then how difficult is it to create that material to work well in that application?
Yeah, there's a lot to unpack in that question. So you're probably going to ask me it again 3 times. Let's try. What I found, because I had that same excitement when I came in, it's like, whoa, this is a polymer that I can use in plastics markets application, fibers markets applications. And what we found is the market got super excited in many cases. That, wow, can I do this with it? Can I do this? And so the early years were pretty chaotic, with many, many requests that we had people wanting to make apparel, carpet, office textiles, home textiles, fiber fill for pillows, fibers for baby wipes, baby diapers, plastic packaging, bottles, injection molded articles, right? And the list goes on and on and on. And some of those, I think we try to be pretty humble because we're a little company, as much as people think of us as biggest bioplastics producer in the world. we're a couple hundred people, and we've been that way for many years. So there's only so much we can do, and a lot of the innovation happens in the channel to market. And on a lot of our work is just trying to support it, fuel it, and fuel it often by simply making the customers in the channel aware. Look, we've got all these different grades. This one can do this. This one can do this, and they do the playing and innovating. So that's a roundabout answer to your question. It doesn't really get to the question, but go on. You ask me it again. You,
No, I think you've covered it pretty well. But I was basically let me add on to the question
sure.
rather
Yeah.
than repeat it. So, are
Yeah.
you governed by the demand on what you're going to focus on in terms of the customer says, "I want more material for packaging,"
Hmm.
or vehicles, fibers, whatever. Is
Hmm.
that what governs your decision on what you're going to produce, or is it generated by what you want to push into the market? How does that work?
It's both. I wouldn't say governs, but what the market's interested for sure is a huge influencer. We want to be responsive and market led. And so part of my job is to quickly see what is happening in the market, a new trend, and see if we can go after it and satisfy that trend, right? Win-win for us, win for the market. At the same time, we don't want to be blind to other possibilities, and so we're constantly looking at what else could we do in a completely independent market. And so some good examples that people don't often think of when they think of, many people think of PLA or NatureWorks and think, okay, packaging plastic. Fair enough. Big part of business, important to my performance packaging business. But there's a lot of innovation out in the market happening that's now become a mature market, which is nothing to do with packaging or even plastics. It's, it's the oil field industry looking for a material that would degrade at the right time temperature underground to help improve the efficiency in which you get oil or gas out the ground. And often in the past, that oil field industry is used as sort of a concoction of odd chemicals, a lot of often controversy about what they put in the ground. And so what we found is we could design grades for that industry that would design at the right time temperature underground, sometimes in days, sometimes in hours, and it helps them basically improve the yield of the oil field and get more oil out. And it degrades and it makes lactic acid, which is occurs in nature. So that's a completely different industry that had we not been humble and listened to the needs of the market, we might not have seen was there, right? Because we thought, well, we make a plastic. What can you do with plastic? But one example.
Yeah,
So
yeah,
I was going to
yeah.
say
Keep
that
going. Keep going. Yeah.
the raft of products. I think that there's most of them make sense longer term. Some probably there's a time and place for them, and so because there's a lot more development needed, more technical applications. So one of the things I started leading was fibers development in the company, and we had a big development focus on carpet fibers, um, on apparel, on home textiles, for example. That continues at a lower level. It's a much more technical market. I think that's something that we as an industry look forward to coming back to and designing grades for in the future. But right now, the major focus for us is in markets like packaging, like nonwovens, fabrics and nonwovens. Huge interest from the global diaper industry for getting fabrics that are both renewably sourced and can have maybe different degradation characteristics. Uh, Polypropylene, a fabric that's used, say, widely in the diaper industry. They're looking for replacements for that are soft, that perform appropriately, that behave right in terms of getting that liquid away from the baby's skin. That's a pretty technical application and one we can do pretty effectively because it's you put pellets into a machine, you get a fabric out. So that's a highly efficient step we can address, very different than the textile industry, which is you put a pellet in, you might get a fiber out, you've got to make a yarn from the fiber, and you go to a mill, a knitter or a weaver, and then you dye or finish it. Long channel. I love it, right? I wear that channel's clothes. You do too. But it's a more complicated one, and so I think it's one that will take longer to develop. So there's these multiple different markets moving at different speeds.
And there must be, of course, a big team or development team that, because these are all complicated things that you're talking about in terms of, I'm sure there's enough modification that is needed in order to get there. So do you want to highlight how the R&D happens?
Yeah, and I would say we're humble. We wish the team were bigger. Look, we're a small team, and a lot of what we do, our focus is on what we can do to make a difference, which is often designing the polymer and the lactides and how we combine them and how we put other species together, which is why we are the polymers together in our products. I'd love to talk more about our CJ partnership to get PHA into the mix. So our team tends to focus on that. We have a small team, applications development that interfaces almost 100% with the market and helps fuel the customers' innovations. So when the customers, often they're global scale multinationals, they've got huge packaging teams. A great example that I want to give credit to is a company like Pepsi, that back in 2009 took a huge step and introduced a compostable snack bag. We didn't get it quite right together the first time, but what is it now? Almost 14 years later, they've still at it. They've got a world-class packaging group that's continued working on that, and they could do things we can never do. And so a lot of our attention isn't our little team doing it ourselves, it's supporting groups like that and what they want to do in their trials and getting the right materials into their mix.
And that is going to take us very, very well in the not to this question, but the next questions, because in a way you brought up Brad Rogers, who works with Danimer now,
Yeah,
and
yeah.
and
No,
me on
Brad,
the
well,
PHA
yeah.
side. Let's dwell on that a little bit more, because that was fascinating what Brad and his team did to bring out
Hmm.
PLA early on, as you said, 2009. But what I remember them, the challenge was the brittleness, the rattle.
Mm.
And then how did you do you know did you guys solve that more, or was it more the PepsiCo and their blending that they did? Because I know that eventually they did take out PLA again, and I know they even launched some
Hmm.
bags in India, and they were not the
Yeah,
same rattle. So how did that
right.
work, and why was it so brittle?
Yeah, yeah, that's a great sort of case study we can delve into. So one of the attributes of a PLA in an unmodified form is just a very hard, rigid material. For our listeners, think about sort of a hard, rigid material like a polystyrene, like a CD case. Not that anyone buys those anymore, right? Versus a soft, flexible material like a polyethylene in a bag. Completely different in there. And on that spectrum, PLAs in a natural format tend to be hard and rigid. So not an intuitive thing to make a chip bag out of, right? And indeed, chip bags today are typically made out of one of the soft flexible materials, polypropylene. And so Pepsi sort of took what was at hand at the time, their suppliers, the guys that make film, many meters wide film at a global scale, happened to be our NGO grade of PLA, and worked with it. But in its natural form, it was hard and rigid, and it was noisy when you would crinkle it. We got that. It was clear from the beginning. There was no surprise. Um, they made huge steps towards solving that problem back then, and there were many players at the table. I want to be clear. We were but one. There was the guys selling the adhesives that laminate all the layers together, because the chip bag's a pretty complicated structure. And I think they came up with a softer structure. It sounds like you saw it in your geography. But I think there was still the cost challenge. And so that's when they, with a very long-term view, have just kept working on that over the last decade, formed partnerships with other material producers, and really making good headway. And all along the way, they've trialed other things, they've kept in touch, and really driven a ton of innovation. And so when we put together our collaboration, formal joint development collaboration with a leading new entrant to the PHA industry, a company called CJ, and probably you know them out of Korea, that was hugely interesting to Pepsi and to others. So we did that because we wanted to combine a polymer, PLA, that's hard rigid, with a polymer that's soft flexible, polar opposite, PHA. And when you put those two together, you can really move across the spectrum and adjust the properties. And that's what I was saying up front, that the NGO grades we sell going forward, they're going to use whatever materials they need to get the right properties. Because it's not about introducing a green material and wondering why the world doesn't buy it. It's about matching the functionality that the market needs to make a difference.
Yeah, and of course that leads us to I've I've found this material PHA super fascinating. I've
Hmm.
visited Daniel at RWDC and
Cool.
seen his
Yeah.
process and talked to various other startups who are doing this. And I'm very excited to learn what made you guys think of PHA as a substrate, and how is this? I've not heard of CJ actually, but I'd love to
Hmm.
learn why
Sure.
CJ and what is this the partnership entail and what is the world going to see out of that?
Sure. Yeah, well, then, glad you said that. Let me just back up a step and sort of give a context. CJ is based in Korea, $25 billion giant in the Korean landscape, big multinationally. They've actually got the biggest fermentation assets in the world, 700,000 tons of fermentation assets. So they do this on a grand scale, making different bio-based monomers. So very natural for them to look at what you could do with advanced materials. They're a big conglomerate. They've got CJ Biomaterials. They span many industries. As a local factoid in the U.S. that most people don't know. I don't know if you know Schwann's food delivery,
Yes, yeah.
delivering quality foods. That's owned by CJ, for example. So they're big. And what happened, it sounds like you're well versed in the PHA space, so you probably know the history of what Metabolics did, the joint venture there, building out a world scale facility, maybe a little bit ahead of its time in scale, and it basically shut down. What CJ did back probably around 2014-15 was they purchased the entire technology portfolio for Metabolics for PHA. So access to all that suite of grades
Interesting. Yeah.
that Metabolics started to make. And they took some time, some years, to really map the landscape and understand what they could learn from the past, what other PHA producers were doing, where they should start, how they could align the Metabolics technology portfolio with their own fermentation assets. And what they started up last year, and probably a good candidate for you to pull in future interviews, would be the guys running their biomaterials business. I think it would be kind of a natural for your listeners. But what they built out is a roughly 5,000 ton per year PHA facility in Indonesia, making their first grade of PHA. And it's quite different chemically than it sounds like what you're well familiar with from, say, some of the US producers. This is the PHA that CJ Biomaterials, our partner here, is introducing, is essentially designed as a modifier for PLA. It's not designed to be used on its own. A good analogy it came up the other day in a discussion was if you're from the plastics industry and you think about polystyrene in its native form, not really a performance material. You drop that old CED case, it shatters, right? Hard, brittle. The performance polystyrene is something the industry calls HIPS, high impact polystyrene. It's got a rubber modifier in it, and that's essentially the analog here would be what the CJ's product today. It's called FACT is their trade name. What that FACT PHA does is essentially a rubber-like modifier designed for PLA. And so it was very natural as they were going to market, looking to go to market with something that was designed explicitly to broaden the field for the PLA industry. Well, why not partner with the PLA industry? And that was the genesis for our discussion that manifested itself back last November in this announcement of a joint development agreement, where we supply each other material. We supply them our PLA, they supply us their PHA. We look forward in the future, in the near future, to introducing products. It may be them facing the market, it may be us, but it could well be, imagine an Ingeo grade going forward, for example, Ved, that perhaps introduced to the thermoforming market an Ingeo grade with FACT inside it to adjust its properties so that it gives a more flexible package, and perhaps one that can degrade quicker because PHAs are famous for their quick degradability. So what we loved is this concept of taking a material that the industry is really intrigued with, PHA generally, because of what it can do, because of its quick degradation, and yet which the industry is also a bit puzzled with from a cost point of view, because it's not an inexpensive material. When you combine that with, as a modifier to a material like the PLA that is in our Ingeo grades, you can really get some cost-effective property adjustments, which is what we're aiming at. And our primary joint development focus today is in the rigid thermoform packaging space and in the space of flexible films, where, as I said from the Pepsi example, a natural PLA is just too hard and brittle. But our collaboration doesn't just end there. We've already introduced to the market something that came out of our collaboration very quickly, which was some new Ingeo grades designed to make nonwovens. We've called it Ingeo Soft because it makes a very soft fabric. And we're sampling nonwovens customers around the world now, not in the packaging space at all, but customers that are interested in redesigning, say, a baby diaper. And there was always an interest from the leading diaper brands in materials like PLA, but you make, just as you make a stiff film that you observed in the Pepsi bag 12 years ago, a normal PLA will make a very stiff fabric that's not very nice to a baby's skin, right? So the product we've just introduced, which came out of our collaboration with CJ, it's basically an Ingeo grade that achieves its properties with FACT PHA inside it from CJ. That makes a super soft fabric that's completely bio-based. If it's relevant, could degrade at a different rate, but that's really often not the primary interest of the diaper maker. If they want a performance fabric that's soft, gets that moisture away from the baby's skin, right? You don't want diaper rash. So there's already some cool things coming out of our CJ collaboration.
That's fascinating, and it actually brings up so many questions in my head that I don't think we can cover it in this conversation, but we'll cover a few. So staying with flexible packaging first.
Sure.
Flexible packaging for me personally, and I know various others, has been so interesting because barriers are not easy to achieve, especially when it comes to moisture. Are you guys looking at something like that with this combination? And we found that PHAs, PHBs, PHBVs, they work very interestingly on the barrier space, more so than, like, we found better moisture barriers than many other substrates from many of these. And would you possibly be looking at combining them and creating a non-metallized structure that can hold potato chips? Would that be something that is already in the thoughts, or would that be something that you guys would be exploring?
It's something for the future to explore, I think, as we early days for us in the film market, and we're looking both at the biax film market, which is a totally different process, big machines, right, 10, 20,000 ton per year production rates, hard to go do small scale trials there. But as we're looking at that at the same time that we look at the blown film market, where there's many more players, easier to run small scale trials, different properties needed. So early days, as we're developing formulations that can address those, and we're starting to sample that to the market. We expect to be announcing some things between us and CJ in the future shortly. I think it's fair to say that right now the focus, for sure, there's an ask for better barrier in flexible food packaging. And one of the big barrier challenges has been the technology the industry knows very well, which is the metallization. One of the challenges with it, when you have a very rigid film structure, is you crinkle the bag, it's so stiff, you crack the metal barrier and you affect shelf life, even in transportation. So the immediate win, we think, is to make a slightly softer film, and that seems to be really getting the interest of the film producers, that will metallize better with higher efficiency and have that barrier survive longer, through the life of the package, versus perhaps, in transportation, you bend the bag a little bit in the box before it's unpacked, you have a crack in the barrier. So that's the immediate focus, but what you're saying longer term for sure is of interest. I mean, again, we're humble and we're hoping to learn from the ideas from the channel and help them do a lot of this innovation.
What about monolayers? Do you see there being an achievement of these crazy barriers that we look at, both in terms of moisture and air, being achieved through just a pellet being blown? Is that a possibility at all? I guess we are hitting in the dark, but is that something that has come across your mind already, or your team's mind?
Yeah, we get asked that a lot, and I think it's for sure challenging. And it's we have to often remind people that it's challenging with the incumbent materials. I mean, take another application I love in packaging, not flexible at all, but the coffee capsule, right? The K-cup style that many of us use every day. The world has it in its head that that's shifting to polypropylene because it's recyclable, and the world thinks polypropylene, but it isn't polypropylene, which doesn't have the barrier. Even that and it's a rigid structure, not flexible. It's a multi-layer with a barrier layer in the middle to get the shelf life. So I would say unlikely with any polymer, not this is a general comment, not really about the biomaterials, that you're going to get the performance you need with one layer. It's sort of the holy grail that this polymer will do everything you want, perfect barrier, bio-based, disappear when you're done with it, or be infinitely recycled with one material. Not realistic today with the incumbent materials. So that's not, yeah, just sort of a big picture comment.
Super. And let me switch to nonwovens since you were talking about
Sure.
nonwovens. And then that'll couple also with the next step of degradability, which you mentioned. So are you looking at nonwovens that are essentially degradable? That would be my assumption. And of course, would that mean that eventually these diapers could be disposed in a non-incineration kind of way?
Mm-hmm. We for sure look at that, and everything we develop, we are sort of look simultaneously at the mechanical properties of not only how does it process, but what's the final properties, the softness, the drape, the strength, and so on of the fabric, but its degradability characteristics. Um, as you said, as you acknowledged, the relevance of degradability really depends on the application, and the structures like diapers are pretty complicated in terms of one, what they're typically carrying when you discard them, right? Um, and then when you talk about degradability, is it in an anaerobic digestion scheme where you want to capture literally the feces and the carbon value and methane generation value of that? Um, Probably not compost. And now there are schemes that actually look at taking apart the diaper and trying to chemically recycle some of the components. Um, and I've seen some materials from some of the leading polyolefin producers to sort of hint that's the holy grail. And I struggle a little bit to think that there'll be an industry that separates diaper contents from diaper and recycles the materials. Whew. For things to be adopted, they got to be easy. So I don't know the reality on that one. But yeah, long story short, we look at the degradability characteristics of everything we develop. We want to be articulate in talking to our customers about that and help them make the right choices and help them not make marketing claims that are not authentic, which
Of
so often
course,
happens. Yeah.
yeah. And then, of course, there's that, and I'm sure you sort of butt heads with this every day. There's that whole challenge of industrially compostable versus home
Mm.
compostable, and we get to hear this. No, don't use PLA because it is not home compostable, and there are no industrial composting sites. How do you
Yeah.
deal with that, and what is that story? And is that, I know that you can probably compound it to be home compostable. So,
Hmm.
and so there's various things in that spectrum, and you can tackle it the way you want to tackle it. But I would love to hear your point of view on this.
Sure. Yeah, our point of view, I think, is we fully understand why that ask comes, and there are many folks out there that will spend a lot of time sort of pointing out how little home composting happens and so on. And look, I don't do it. Many don't, but I don't think that's the point. The bigger point, I think, that's really behind the request from the market for home compostability, the bigger concern that's beginning to get articulated when we really dig into it with brands, is not that they want their consumer to home compost. They don't want to put that on their consumer. The bigger concern the brand has in their head, I think, often is persistence in the natural environment. They don't want materials out there that will be around for centuries, like some of the incumbent materials. And often the only claim they can point to right now as evidence that it won't be around forever is a home compostability certification, right or wrong. And so that just feels like it generates, well, feels like an awful lot of oxygen in the room gets used arm wrestling over home compostability. And I think we like to take it to the bigger point. We totally get that the real issue, we believe, is long-term persistence. And that's why we're excited, whether it's a PLA, a PHA, a PLA naturally, whether or not there's, even if you're in an environment where there are no microbes, no active bacteria to do the digestion of PLA, it will, at a definite rate, it will break down with water. It's not a switch that goes on and off. We chemically recycle. We've done this tens of thousands of tons today. Chemical recycle our off-grade materials back to lactic acid by just boiling them with water, and that long chain splits back to lactic acid. That's at a high temperature, it can happen in hours. At a low temperature, it might happen in days or years. but it doesn't take centuries. And so where we like to take the discussion is say, look, isn't what you're really interested in when you talk about home compostability long-term persistence? And let's share the data we have and third parties are generating on long-term persistence, whether it's a PHA or PLA, and show that it's not long-term a material out of place. And I use that language intentionally because I love to hike. When I'm in the woods, if I see a plastic wrapper or candy wrap, it's clearly a material out of place. If I see an oak tree falling down, I don't think, what's that doing here? And yet it takes probably 50 years to degrade, right? Oak. So it's a little bit of context that, yeah, that these materials won't be around forever, that they will, at some time scale, depending on where you are in the country, in the world, they'll degrade back to lactic acid and ultimately CO2 and water, part of that bigger carbon cycle. So, sort of a bit of, I guess, more of a philosophical answer to your question on home compostability. I want to add to that, but go ahead. Yeah.
Yeah, no. I think philosophical, but still practical. I appreciate your answer, and it actually tweaks my interest on this. So what you're saying is that it's just a matter of time, and that's what I'm listening. Maybe I'm not getting it right, but what I'm seeing is hearing is that it is a matter of time. It's not a question of whether it'll compost or not. It will compost, whether. Of course, in India, in the heat, it would compost probably in a matter of maybe much shorter time, and in a colder climate, in the Nordics, it would take a longer time. Hopefully, we won't dispose it in Greenland. So and I guess even the home compostable stuff won't compost in Greenland. So is that what you're saying? So in that case, why is it not just home compostable but a longer time? Is that a test condition?
Yeah. So first, I think you're spot on. You said it very simply. It is simply a matter of time. The point for us is that the materials we sell won't create long-term persistent microplastics. It's a matter of time, and the time depends on India versus Greenland. Back to your point about why not home compost, there's a definite time scale that has been associated in certifications that are being developed in Europe and now in the US that define the time scale for home compost. And we're not blind to that. As much as I gave you the sort of big picture philosophical answer, we are right now, today, especially through our joint development with CJ, we're developing materials that will pass that test. And we're pretty excited that we think we've got something coming for the blown film market, which sounds like you know quite well, that will be home compostable with the existing standard. But as much as we're excited that we can actually meet that standard, I always go back to the bigger point that, how much of it will actually get home composted? Probably very little. The bigger point is that it should be industrially composted or recycled, and we could talk more about some of the advanced recycling schemes we're experimenting with. The point is that if it accidentally ends up in the wrong place, a material out of place, like that candy wrap when I'm on the trail, it isn't going to be there forever.
So what I'm hearing is that it's basically a test issue. Somebody decided that this is the test condition, and in order to be called home compostable, you will have to meet the test. Otherwise, it's just a matter of time. And of course, now what you mentioned again is something that I would love to talk about, the whole recyclability idea. The challenge that I find personally with materials like PLA is they look so similar to polyethylene, for example, except obviously they're not as soft, but otherwise, appearance-wise, as a consumer, it's very difficult for me to segregate the bins. I'm hardly being able to segregate the bins within, like even metal and plastics. And then to say that segregate the bins between a PLA and a plastic seems to be a challenge. So how do you see that? Do you see consumers actually segregating it, or even the sites for recycling? It's probably difficult for them to do it, considering that it looks pretty much like plastic. And how do you resolve something like that?
Yeah, to your question, do we see it happening? It really depends on the geography. Certainly in some European countries, there's multiple bins. There's a green bin, and the consumers grew up with a totally different culture, much like you and I did, and they're used to it. And they take care with that waste stream. Tough in the US at the household pickup level for sure. Where we've seen the best success is in venues, sports venues specifically, where that venue has total control over what goes in, so it can all be compostable and perhaps recyclable if it's a bottle. And there's 3 bins, and and ideally 2 bins: compost, recycle, and there's no hesitation. You know what to put where. Tough at the consumer level, and the consumer level, how we have frankly worked hard to acknowledge the challenge is by staying out of the lookalike applications largely. And a good example is the bottle space. I mean, early in my career in performance packaging, a lot of excitement around, well, you could make a wonderful replacement for a bottle. Injection stretch, blow molding is the process. PET is a wonderful material there. Look, as you heard, I came out of the PET industry. I think it's a great material. It makes a nice bottle, a bottle that's largely recycled in most geographies. So that, to us, that's not a great fit for a PLA that looks indistinguishable. Doesn't make a bottle, by the way, with a good long shelf life because the water diffuses out. So we've largely stayed out of that because we don't want the consumer getting confused, and we don't want to contaminate a PET bottle stream. So we focused on markets where that recycling isn't happening, unfortunately. And the fact that it isn't happening lets us build to a scale where we've got enough PLA-based articles in there that we can then start to pilot recycling schemes. And we work hand in hand as an industry here. I think you heard probably from Tomas Philipp on what they're doing. We're sort of building off each other here with trials we've run, trials they've run, and really as an industry association trying to address this issue for the PLA industry.
Just a follow-up question on that, because there's so many people on the consumer end compounding with different materials and PLA and their own experiments, and you want that to happen. How does that affect recyclability? Because you'll get a multifarious kind of amounts of products that are going to come into your stream, and then of course you're going to try and convert it back to lactic acid, but it'll have impurities. And how does that affect your recycling process?
Yeah, it's a great question, and what we're excited about is I don't know if you know NREL, the National Renewable Energy Lab in Golden, Colorado. They have a very interesting program right now with some big brands backing them, where they're looking at exactly that question and doing some work to look at sort of the holy grail of wanting a package that's bio-based, recognizing that it may be multi-component. I don't know if I use the word nefarious, but it's got a bunch of nice bio-based materials in it to get the properties they want, and looking at advanced recycling schemes where they can break that back to the relevant monomers and separate them. Sounds a bit, very idealistic, but I love the fact that they're doing it and they've got some big brands behind them and they're presenting at conferences around the world. I mean, I can certainly point you at them perhaps if you're interested, because that could be an interesting good garbage topic going forward. But it really gets at longer term, recognizing that there's not a silver bullet, one material that'll do all this. It's going to be combinations, and then you've got to, as you scale the combinations on the manufacturing side, you've got to scale how you're going to recover them.
What do you think about combination with paper? I'm seeing a lot of possibilities emerging with cellulose kind of substrates, and it could be a more dense, non-porous sheet of paper and different barriers coming in. How do you see those areas evolving and different applications being developed from there?
Yeah, I'm glad you asked that, because my colleagues would probably be beating on me if they knew I hadn't mentioned paper. It's a really exciting focus for my performance packaging business because we have a major focus now on developing grades for paper. And we were out there now for a couple of years with an extrusion coating grade, you may know. I know we worked with some of the Indian producers because the hot cup, for example, that we take for granted at our local coffee shop, seen as a paper cup, but as I'm sure you know, lined with polyethylene that's been optimized for 50 years, and it works really well as a barrier. But if it ends up in compost, it puts polyethylene microplastics in the compost. If it ends up in recycle, that can create polyethylene gummies that mess up the paper pulping process. What we've done is develop a grade there, and it's been commercial for 2-3 years, that starts to coat in a way much like polyethylene. You want a thin, lightweight coating. And so our ideal, and some of the current customers we serve are already there, is a cup that can be composted or paper recycled. depending on whether it's thrown away empty, which is typical for a coffee cup, or food contaminated. And we've worked with a coalition like the Sustainable Packaging Coalition to develop a consumer label. They've had the how to recycle label for some years, they have a how to compost label, and they have combinations of that basically say, and it's in use on something like the cup, that hey, recycle if clean, compost if contaminated. And that's sort of the best of both worlds to us, that you're trying to make something that's robust to the consumer environment wherever it's being used.
And I'm sure there are many, many other applications, and but I won't get into those in terms of, and just for keeping cognizant of the time.
Sure.
But I'm going to ask you some more quick questions, and you've mentioned
Sure.
parts of this, so I want to make sure that that we cover these. So you mentioned sports stadium, and I saw that the city I live in, Portland, you had a green sports alliance. Is that to do with trying to work with stadiums, or why is that?
Yeah, yes, I'm glad you brought that one up. That's been a 10-year partnership for us and really critical because, again, I hope this has come through. My personal passion is how we scale to make a difference. And early on, we saw the Green Sports Alliance as a really good way to do that, to where we could move from just being the guy that makes the resin to working with a thought leader in the space. And there's a slide that the Green Sports Alliance used, and I can't quote the numbers exactly off the top of my head, but it really makes the point. Something basically shows that I think 90% of US population at least follow sports. 10% follow environmental issues, right? And it sort of says it, that if you come at things through a sustainability lens, you're not going to grab the public's attention. I remember presenting that slide at a bioplastics industry conference, and I could just see the look on the faces of all the bioplastics producers just going, yeah, that's the problem. It's like, no, that's the opportunity, that if you want to get consumers' attention, sports is the way to do it. It's a universal language, right? Everybody follows sports. Cricket, Man United in the UK, right? Barcelona, everybody follows sports. If you want a platform to drive change, that's the one. And that was the genesis of our relationship. I just came back from a week in Seattle, Green Sports Alliance Summit 2 weeks ago, always charged up from that group because they can make a difference. And so our partnership with them is really about being sort of a materials advisor, because we don't sell to them. The channels we sell into, many of them converge on the field, right? Not just the food serviceware piece, the plates, the cups, the cutlery, but lots of channels, supply channels converge on the sports field. And so our work with them has involved pointing them at the latest innovations coming out of the channel, ours or others. We just, for example, pointed them at something very cool that M&M Mars is selling, developing a compostable chip bag, and got them excited. And we haven't been directly involved in that, right? But we're excited nonetheless about the fact that it's a compostable chip bag. And we show that to the Alliance members who run the managers that run the venues, that run where the Portland Trailblazers play, for example. Because they can specify everything that goes into their stadium and make a difference. And to be clear, their focus isn't just waste, it's water, power, electrical usage for the stadiums, and waste. Our intersection is most clearly on the waste end, and how we turn that into a better garbage stream, if you will.
And you're also the Bioplastics Council's chair. And what does that role entail, and how are you building that momentum through that role that you play?
Yeah, it's actually, I'm not in that role currently. I was in it for many years, but that was basically representing, if you will, the bioplastics industry as a little division of the bigger plastics industry in the US, which is a huge 10-year, decades-long industry. All the plastics producers are converters, sometimes the brand owners. And I think that industry association, it's now called the plastics industry, the association was glad to sort of make home for, if you will, the bioplastics industry, recognizing it as a legitimate player that was satisfying many of the producers also were now producing bioplastics, like a BASF, for example. Some of them, like ourselves, were a bioplastics pure play. But our point there was to join the bigger plastics conversation and be a part of it, instead of sort of setting ourselves up as plastics, bioplastics, in opposition. No, we want to work change from the inside. And so we've often, through that Plastics Industry Association, advocated together for change that's good for the industry and change that's often material neutral, but it kind of creates a level playing field for conventional plastic, if it can be recycled, or compostable plastic. And again, it's about a level playing field versus advocating for any one particular material.
Yeah, I agree with you. There's no, like, this whole idea of just activism from the outside. It's very
Right.
difficult to work. It's
Yeah.
better to activate
Yeah.
from the inside. Of course, I have to
Yeah.
get to this question before we move towards closure.
Yeah.
The one of the things, and you mentioned it as you were talking about it, that, and for me again, it has been very, very important that we look at scale, because the size
Mm.
of the challenge is large. If you're going to do little plants, and all those are needed as well, but there is at least a few needed at real scale so that we can make a huge impact.
Mm-hmm.
So two things from that observation is that what is the scale right now, and of course adding the Thailand facility then, and then what are you looking at as you grow? And I'm going to combine that with another part, which is the cost side. And I know
Mm.
that you guys have already brought the cost down significantly. And how do you see that evolving in the future? So scale and cost.
Sure. Scale and cost. I guess by the numbers for ourselves, our scale, I'll give you the numbers, then I'll give you the context. Our scale is a 150,000 ton per year facility in Nebraska, a factory starting up in 2 years in Thailand, half that, 75. That's our piece of the bioplastics world. The total bioplastics world, material made directly from bio-based carbon, is less than £1 billion. Small, right? Um, Compare that with the conventional plastics industry. And I'm not going to get these on the same units for you, but it's 300 million tons per year. It's huge. So that we're, percent, single digit, small fraction of that overall business, which is both an opportunity and for folks like me, like the idealistic kid that wanted to make a difference, right? It's frustrating. Like, how do we scale more quickly? And I think how we do it is by focusing, not trying to be all things to all people. In spite of this industry's, the market's huge curiosity. Wow, can I do this? Can I do this? Can I do this? It's focusing, where can I go where I really make a difference? Uh, where we can have a big difference on a piece of the market, a niche of the market, but still big to the bioplastics world. And that also addresses your question about price and cost, because this conventional industry, 300 million ton per year, has an immense economy of scale, all the way from the oil well to the monomer production to the polymer production. An economy of scale often helped by incentives for the oil industry, right? To be frank. So how does one compete with that? Difficult. We did an interesting calculation years ago, and I remember our CEO presenting at a conference and making the point, look, I could give my material away for free. And by the time you, customer base, get it to the retailer, it would still cost more because of the inefficiency of scale at the guy making the sheet, the clamshell, and so on. So just realistically acknowledging that, and knowing that we have to have some interesting profit in order to be able to reinvest, means that we focus on where there's value to be had for us and the customer, where there's really a value to compostability. And so it's not everywhere. I don't believe all cups in the US should be converted to be compostable, right? For sure. It's where there's the infrastructure, and that's what we love about the relationship with the Green Sports Alliance, is we're working to bring cost and price down, but at the same time, there's got to be some reinvestment economics for the industry, and it's balancing those. That's what makes the job of the business leader fun, frankly.
And you'll be happy to hear this, because I remember years back we were going to launch our molded fiber products that we make in our company, and we just thought that we cannot package it in plastic after all the
Mm.
hard work that we've
Yeah,
done. It cannot.
yeah.
And of course, we contacted your India partner, and we said, you have to supply us PLA, and it was 3x the cost then.
Mm.
And I remember having this argument in our board, where our board said,
Mm.
"Are you crazy? You're going to pay 3x for packaging?" I said, "There is no question. There's not even a
Yeah,
discussion there, because
right.
you can't just tout this idea that you're trying to create something which is going to be beneficial, and then package it in something that you're
Right.
trying to, in a way, go against. And now it's not that different. The costing is pretty similar over the last 3 or 5 years, actually. It's come down significantly. And that's also to do with playing with the thickness and maybe the compounding that
Hmm.
the guys have done here. But it's been
Yeah.
fascinating for me to watch and actually root for you guys because, that's really, I've seen
Yeah.
it practically happen that it's not that
Yeah.
different. Maybe we are at about 1.4, 1.5
Hmm.
times now.
Yeah.
Not that different at all. So thank you and congrats to you for that. And that, of
Yeah.
course, anything that you want to add further, of course, that, and then taking me to my final question, which you
Sure.
started with right on, is what is good
Yeah.
garbage to you? But yeah, before that, anything else that you
Yeah.
want to add? Then of course,
Yeah,
I'll
just
ask you.
building off your point, and I really appreciate you making it instead of me saying it, but I spot on. I agree with you, and we like to get beyond just the direct material comparison, which you have to do, of course, but look at the cost of the solution, and that can sound good, but be really hard when you're talking to a buyer. But an easy example to get your head around, and you alluded to it, is you can compare PET, for example, versus a PLA cost pound for pound, but you can't ignore the well, this is very valid for us in the polystyrene world when we're supplying into yogurt cups, typically HIPs, high impact polystyrene. You got to look at the extra stiffness. That thing that made it a little challenge for a Pepsi bag being stiff and noisy is an advantage in a thermoformer because it's stiffer, you can make it thinner. So you got to look at the cost of the finished article, and that's easy for a producer to get their head around. Another example too is in more complicated structures like a baby diaper where you've got performance fabrics, you got pulp to absorb the liquid from the baby, and you've got a super absorbent, that stuff that swells up, right, and absorbs the liquid. We found that the right combination of performance fabrics can actually let you use less super absorbent. So yeah, you may pay more for the fabric, but you got to look at the system cost eventually. And so love the way you framed it, and we like to take it back to the fact that you can't be a one-dimensional comparison on just the cost of the polymer, or you don't do anything. But then to your last question, yes, say it again on the good garbage.
Go ahead. That's basically what does it mean to you as a person?
Yeah.
What does good garbage mean and what does it look like?
Yeah, so how do I define good garbage? It's funny because if I go take you back to that story in up front about that little kid that was pulling stuff out of the landfill, right? And I hadn't connected the dots until I sat down and looked at the question. So I really appreciate it. That little kid saw garbage for what it was. It was a rich material stream, right? And in the future, so we won't even have to ask this question, what's good garbage? Delineate good garbage from bad garbage or garbage, because we won't be talking about garbage streams. We'll be talking about raw material streams, which, hey, this kid saw when he hauled that Coke machine home, right? I got the look from his dad. So, yeah, for sure that's idealistic, that we don't even have to ask the question. That's decades out, probably beyond my lifetime, but I love where we're going when we look at garbage as not garbage. The word doesn't exist. It's another material stream. And so along the way, yeah, we're going to have to characterize garbage streams by good or better garbage streams are going to be those that don't have species or things in them that stop them getting reused. Don't have nasty species, for example, or things like the fluorinated materials that are getting banned. That makes them, stops it being a material stream that can be reused. Don't have the PFAS. So I think I gave you the long term. We're not even talking about garbage. It's just another material stream. Short term, yes, we're going to have to start to grade out that material stream as to what's good about it and start to get the bad things out of it that stop it being a usable material stream. Hope that makes sense. And I love the
Absolutely.
question.
And I love the answer. Thank you, Steve. This has been a fascinating discussion. You have no idea how much I've skipped. And it was like breaking my heart because I wanted to ask you so many things. I can see my notes. It's like things like melt flow index. There's
Oh
things
boy.
like other combinations,
Yeah.
and like
Yeah.
why does it flow like that? But I'm going to
Yeah.
we're going to have a follow-up conversation
I'd
sometime
love
on
to.
this.
Yeah.
So
Yeah.
thank you so much for taking the time for being on the show and joining us and illuminating us so much about these materials. Thank you so much for being with us.
Sure. I appreciate the passion, the opportunity to let my passion shine through. I love the question, so thank you. Love to do it again. Thanks, man.